Okay, so problem 8.6, calculate the following limits using Taylor's theorem. Okay, so here the idea of all these limits is to actually use the approximations that we can get for all of these functions using Taylor's theorem uh, to actually solve this into the indeterminations. Okay, so all of these limits are going to be indeterminations. Okay, for instance, let's start with the first one. This is the limit when x goes to 0 of e to the x minus the sine of x minus 1 divided by x squared. Okay, so this is 1 minus 0 minus 1, 0 divided by 0, right? So this is the typical thing that, so all of these probably are going to be 0 divided by 0. And this is the typical field where the students of calculus typically try to apply L'Hopital's rule. And in this case, you can apply L'Hopital's rule and it's going to be easy enough, right? In some cases, though, L'Hopital's rule requires repeated iterations before you get to something useful, right? And so that's why we're going to see how applying Taylor's approximations can actually make this kind of problems way easier, right? So how do we do this? First we approximate, we write the Taylor expansions that we know for this function. Okay, so e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus blah blah. Okay, and the sine of x is going to be x minus x cubed divided by 3 factorial plus x5 divided by 5 factorial and so on. Okay, now the idea here is that, as you can see, just looking at the first terms, right? So e to the x is 1 plus x, right? Minus the sine is minus x, so x and x cancel out and you get minus 1, so 1 cancels out, so you get a 0, right? So what you want is to approximate to the next term, which in this case is x squared, and in order to get rid of the determination, in general, you're gonna want to approximate up to the term, the order of the denominator, right? So in this case, it's up to x squared, and just add the terms in small o of x squared, right? So this is going to be like this. This is the limit when x goes to 0, and then this is e to the x is 1 plus x squared divided by 2 plus small o of x squared, right? And then we have minus the sine, which is minus x, minus, and then everything else is small o of x squared, which we have it here, so it's okay, minus 1, and then we have x squared, right? And as we said, 1 minus x and x cancel out. What you have is x squared divided by 2 divided by x squared, so this is 1/2 plus, and then the limit when x goes to 0 of small o of x squared divided by x squared. And the limit of this is obviously 0, because that's the definition of small o of x squared, right? So the limit is going to be 1/2. You see? So in this case, using L'Hopital's rule, we would have had to differentiate twice. In this case, we don't need to. We just need to apply our Taylor expansion once, and that's it. That solves the problem. This shows you the power of this approach to solve these problems. Okay, let's see another one. The limit when x goes to 0 of the sine of x minus x plus x cubed divided by 6, all of that divided by x to the 5. Okay, and as you can see here again, the sine is going to be x minus x cubed divided by 6 plus x to the 5 divided by 5 factorial, which is 120. And if you compare here the expressions, this is x minus x and x cancel out, x cubed over 6 minus this cancel out, you have x5, so you can get rid of everything else, right? You don't need the terms after x to the 5, you don't need that. So what you're having in the denominator, x5 over 5 factorial divided by x to the 5, which is 1 divided by 5 factorial, which is 120. Okay, so you see how these things are very, very useful. The third time is the limit when x goes to 0 of the cosine minus the square root of 1 minus x divided by the sine of x, right? And now let's see, so the cosine we know is 1 minus x squared over 2, and well, let's see if we can get things just with the x squared, right? Now we have the sign. We already know this is x plus the next term is x cubed, so this is small o of x squared. What happens with the square root of 1 minus x? Okay, so let me write this again. So this is if we approximate this is at 0, right? This is f at 0, which is 1, plus f prime at 0 times x, plus the second derivative at 0, which times x squared divided by 2, right? And then small o of x squared, right? What is the derivative of this? The derivative of this is minus 1, the derivative of this divided by 2, 1 over x, or in other words, this is minus 1 half times 1 minus x to the minus 1 half. And the second derivative is going to be minus 1/4, sorry, minus 1 half times 1 minus 1 half, which is 1/4 times minus 1 minus 1/4 times 1 minus x to the minus 3/2, right? And let's see. So this is going to be, now we can compute this. This is f prime at 0 is going to be minus 1/2. And the second derivative at 0 is going to be minus 1/4. So the approximation for the square root of 1 minus x is going to be 1 minus 1/2 of x minus 1/4 divided by 2 minus 1/8 of x squared, right? So this is 1 minus x squared divided by 2 minus 1, and then we have what? Plus 1/2 of x, right? And then everything here with this is plus 1/8 of x squared, and then all of this is plus small o of x squared, and in the denominator we have x plus small o of x squared. And as you can see here, we actually didn't need to go that far because there's a relevant term in x here that the cosine doesn't have, right? So all of this term, and this term are small o of x. So we can rewrite actually this like this. This is 1/2 of x plus small o of x divided by x plus small o of x, right? So we divide everything by x and compute the approximations. We get is that the limit is 1/2. Okay. Now let's see. Part 4. Part 4 is the limit when x goes to 0 of the tangent of x minus the sine of x divided by x cubed. So we know we have to write to x cubed, and so the tangent of x is x plus 1/3 of x cubed plus small o of x cubed. The sine of x and the tangent, actually the approximation of the tangent is useful to remember it up to third degree, right? So these two terms, it's useful to remember. In the case of the sine, it's just easy because it's just alternating the parts of the exponential, right? So it's just x, the odd powers, and changing the sign, and that's it, right? So this limit is going to be x minus x. You cancel that out. You have 1/3 minus 1/6, or in other words, you sum the two of them, you get 1/2, and so this is 1/2 of x cubed, right? Divided by x cubed, and this is 1/2. Okay. Okay. Let's go to part 5. The limit when x goes to 0 of x minus the sine of x divided by x times 1 minus the cosine of 3x, right? Now the sine, obviously we need to reach to x cubed because otherwise the denominator the numerator is going to be in terms of is 0, right? And then we have the cosine of 3x is going to be 1 minus, and then this is 3x squared divided by 2 factorial, and then plus small o, and the next term is x to the 4th, so it's small of x cubed, right? And this is 9/2 of x squared, right? So if we write this, this is the limit when x goes to 0 of x minus x. You have x cubed divided by 6 plus small o of x cubed, and then here you have 1 minus 1, 0, minus minus plus, so this is 9/2, and then this is x squared times x cubed, plus small o of x cubed. So this is x cubed and x cubed go away, so you have the limit of this is 2 divided by 6 times 9, so this is 1/3, so 1 divided by 3 times 9, 1 divided by 27. Okay. Let's do part 6. This is the limit when x goes to 0 of the cosine plus e to the x minus 2 divided by x cubed. And again, so we want to reach to x cubed, right? Because otherwise we are gonna be left with nothing in the numerator, right? So x cosine is 1 minus x squared over 2, and then plus small o of x cubed. The exponential is 1 plus x squared over 2 plus x cubed over 6 plus small of x cubed, right? So then we have the limit when x goes to 0, and then you have 1 plus 1 minus 2, you get rid of this, right? The x and the x go away, x squared over 2 and x squared over 2, so the denominator is just x cubed over 6 divided by plus x squared, all small, always x cubed divided by x cubed. The limit of this is 1/6. Okay. Let's do part 7. This is the limit when x goes to 0 of 1 over x minus 1 over the sine. And let's see. So there are many ways to do this, but maybe one way to do it is to put everything in the same fraction. So this is the sine of x minus x, and as usual we know that the sine of x is like this, x minus x cubed divided by 6 divided minus x is just the x cubed part, right? And then you have the division, and then x is the x, you have x squared, right? And then everything that's small o of x squared, right? So if you want, this is which also small of x cubed, sorry, right? So then what you have is x divided by 6 in the numerator, right? So this is going to be equal to 0, right? So it's an important, you see how powerful this technique is, and the important thing for me is that it allows you to understand how some functions behave similarly like others, right? Okay, so this is 1 over x times 1 over x minus the cotangent. The cotangent is 1 divided by the tangent, and using the same technique as we have used, let's express everything in the same fraction. So this is x squared times the tangent, right? X that multiplies this, and then you have here is the tangent minus x, and the tangent is x minus, and sorry, plus 1/3 of x cubed plus small o of x cubed, right? And so the limit when x goes to 0, then you have 1/3 of x cubed plus small o of x cubed here, and then again you have x squared times x, so this is x squared plus small o of x squared, sorry, this cube, so you have 1/3. Okay, so then you have the limit, let's say part 9, the limit when x goes to infinity of x to the 3/2 times the square root of x plus 1 plus x minus 1 minus 2 the square root of x. Right, now the problem here is that we don't have really an approximation for these functions when x go to infinity. We do have when x goes to minus infinity, actually, right? Sorry, not minus infinity, it's 0, right? So what happens if we try to let's see. So this is the this is x times the square root of x, right? So you can actually multiply the square root of x with this all of these terms, right? So this is the limit when x goes to infinity of x, and then you have the square root of x plus 1 times x, so you have x squared plus 1 plus x squared plus x squared plus x, and you have x squared minus x minus 2x, right? And then what you can do is or maybe you can have done it from the beginning, but whenever you have limits when x goes to infinity, you can rewrite this as a limit when this function, sorry, this variable y goes to 0, if y is 1 over x. So then you have here, this is the square root of 1 over y squared plus 1 over y plus the square root of 1 over y squared minus 1 over y minus 2 divided by y, all of them divided by y here, right? So now this thing is going to be, the first thing is 1 over y squared plus 1 over y. You take everything in the same denominator, you have 1 plus y, right? And if you have the square root of this, this is the square root of 1 plus y divided by y, right? The same thing for this. So this is the same thing as the square root of 1 plus y divided by y. This is the same thing as the square root of 1 minus y divided by y. And then here, this is minus 2, right? So this is the limit when y goes to 0 of the square root of 1 plus y plus the square root of 1 minus y minus 2, all of this divided by y squared. Okay? Now, we have seen the approximations for the square root before, right? This was 1 plus y squared minus 1/8 of y squared, if I remember correctly. Or, what was it? Yeah. And then plus smaller of y squared. And then this thing is 1 minus y, minus y squared minus 1/8 y squared, right? Plus smaller of y squared. Now you write this here. This is the limit when y goes to 0 of 1 plus 1 minus 2 goes away, y over 2 minus y over 2, and then you have minus 1/4 of y squared plus smaller of y squared divided by y squared. So the limit of this is minus 1/4. Okay. And then let's do the final one. Again, we have a limit when x goes to infinity, this is 10, of x minus x squared times the logarithm of 1 plus 1 over x. And again, we don't know how to approximate these functions when they go to infinity. Well, we could, but the approximations that we have learned are mostly about centered about 0. So this is the limit when y goes to 0, and then you have 1 over y minus 1 over y squared times the logarithm of 1 plus y. And if you express all of this in the same fraction, this is the limit when y goes to 0, y minus the logarithm of 1 plus y divided by y squared. And again, the logarithm of 1 plus y is y minus y squared over 2, and then smaller y squared. We're not going to need anymore. So the limit when y goes to 0, and then this is y minus y goes to 0, minus y squared is y squared over 2 divided by y squared. The result of this is going to be 1/2. Okay.